Hi guys, in this video we're going to cover a Manova in R. So Manova is an extension of the ANOVA designs for multiple DVs. So it's considered a multivariate analysis of variance. And it's really used when you want to examine the relationship of the IVs to two or more dependent variables, but two or more dependent variables that are related. So regular ANOVA is for like one or two IVs and one dependent variable. Manova is where we have like a combined dependent variable. So you might have multiple measures, like let's say the big five. And you might combine that into personality. It will always help in this analysis if the DVs are related and they make sense as one giant kind of underlying latent variable. If that's significant, you can then break down and see where in each IV the D is affecting the DV. So we've talked before in our previous videos about ANOVAs followed up by post hoc tests as a way to break down the individual either level or condition means. Manova allows me to combine DVs, and then I would follow that same process. So essentially it's Manova to ANOVA to post hocs, and you sort of stop when it's not significant. And it's kind of a type 1 error control because it allows me to stop and not follow up a test when there's a non-significant DV. And so in that case, I would not be running ANOVAs that I knew were not significant. So some brief definitions that hopefully you've kind of got under your belt, but IVs are independent variables. In this particular type of design, this should be categorical in some way. You might group people, or you might experimentally manipulate that variable. Our dependent variable needs to be continuous, or you might be better off doing log regression or chi-square analysis. And that's where we're expecting to see these changes based on groups. And then here's the new thing that's different than ANOVA is this DV combination. So you'll see on the output, it'll say Wilks lambda, Roy's largest root, Hotelling's trace, and Pali's. These are all measures of ways to combine the DV. And what happens is it combines the DV in these linear ways. So linearity is going to be an important assumption that kind of creates these like giant overall means. And it does this in a way that creates the largest group differences for your IVs. So it's kind of like if I created an overall personality score out of all five of the big five measures. It doesn't just average them though. It's a linear combination of them. And the most commonly used one is Wilks lambda. Excuse me. So we can do a couple of different types of Manova. So we can control the number of IVs. So we can have one IV or multiple IVs. And that's the same kind of rules as between our regular ANOVA. So we have between subjects and repeated. You can use two or more DVs, right? And so sometimes instead of analyzing mixed design, people will use Manova to analyze the repeated measures levels. But then you wouldn't want to compare the repeated measures levels to each other. So if you're really wanting in a mixed design to compare repeated measures levels, do a mixed design. I would also argue that a mixed design is going to be better at controlling error rates because it controls for correlated error differently than Manova. Generally, people do between subjects Manova because you treat the repeated part as a separate DV, but you can do repeated measures and mixed Manovas as well as ANOVA. But if you're going to do any type of mixed or repeated design, be sure you follow up with the right type of repeated test. Sometimes these doubly repeated designs are called profile analysis, but it's really just a giant repeated measures ANOVA with special terms. So our process is going to be Manova. If that's significant, break down the DVs and do separate ANOVAs. If those are significant, break down and do post hoc tests. If that ANOVA level is not significant, we're not going to analyze the post hoc test. If the interaction is significant, we're going to ignore those main effects because that reduces type 1 error. And like we've said 1,000 times, if you're interested in the interaction, why would we only want to look at one variable at a time anyway? And really just making sure that you follow up with the correct test type. So don't run dependent T on a between subjects factor. And really you can look at your old ANOVA notes to think more about following up for ANOVAs in case you haven't quite got that down yet. So we're going to do a 2x2 between subjects Manova. So this is going to be a factorial design where I have 2 levels of each of the IVs and multiple DVs. This example is from the Tabachik and Fidel book. And so people were measured on their femininity and masculinity and categorized into low and high for each of those. So this is our 2x2 part of the design. Then we measured a couple of DVs, self-esteem, attitudes towards the role of women. This is kind of barefoot in the kitchen kind of questions, and neuroticism. So we might consider this attitudes or personality. We have to have kind of a term to talk about the overall DV. And so our research question might be if our different feminine and masculine groups are going to score differently on those personality measures, which is the combination of our DVs together. Can I close the door here since the washing machine sounds like it's about to take flight? Let's try some power analyses. So again, we're going to use G-power. And with G-power, we're going to change this to F-test. And then there is actually one for Manova. So we're going to come down here. There's a bunch of different Manova options, but probably special effects and interactions because we're usually looking for that interaction. Okay. That effect size output is very similar. We're going to click determine and use eta square to estimate. Polize V is going to be part of our output, but it's still easiest to calculate from eta squared. So that's something new. Let's hit determine here. So you have some different options here, but what we're going to do is just fill in 0.25 maybe. Let's see, what did I decide? A medium effect size, so eta equals 0.09. The number of predictors, we have 2 predictors. And the number of response variables, we have 3 DVs. So we're going to calculate transfer to main. Alpha is 0.05, power is 0.8 in this example. Let's go back over here. Number of groups here is the number of levels or conditions. It kind of depends on if you're looking for the interaction or the main effects. Here I'm looking for the interaction, so we're going to do 4 groups. Number of predictors 2, number of response variables 3. It's going to be the same thing as over here. Let's enter. So I've got 73 people for our and with a medium effect size. So we need 73 people to find a medium effect. Okay. And the most confusing part of that one is that it doesn't say eta or r, and so Polize is just a different version of that. So if you can remember that, you should use the same eta rules that we've been using before. And then the number of predictors is always IVs, and the number of response variables is DVs. All right. So let's pop over to R here and get started. So let me clear out everything I have been doing where I tested to make sure this ran first. And I'll make this a little larger. All right, so I'm gonna load my data set. And this data set has more variables than I need. So I'm just gonna drop those extra variables and start with accuracy. So our accuracy, we've got a case number here. That's gonna be a subject number. So we're gonna hang on to that because for ezANOVA, remember we need subject numbers. I have my femininity and masculinity variables up here to already be factored, so that's good. My esteem, attitudes, and neuroticism should not basically be negative. Now I do see that I have some NAs here, so we'll deal with that in a minute. And each scale has a slightly different maximum, and we're just kind of assume those are okay, because I don't actually remember what those scales are. With that summary function, I can see I have missing data, but we're just going to check and see what that is by percent, by person. And I already know it's going to be more than 5%, but with our data screening code that we had before, we can adapt it as we need. So I'm going to run my little function here. Remember, this function calculates the percent missing by row or column. Here I'm going to exclude that case number variable because it shouldn't, participant number shouldn't count. It's something I added manually. And we're just going to calculate the percent missing by person and a little table of that. So our 62 NAs here, that's 20% of their data. So we're just going to totally exclude them. So by running a subset on my master data set, where am I missing, basically taking everybody less than 5%, that's going to exclude all of that missing data. So we lost 62 people to missing data. All right. Now for outliers here, since we have several DVs, we have several columns. So now we can use anovas. And remember, for anovas here, we're going to drop that all of our categorical columns. So I'm actually going to drop 1 through 3, because if I look at the data set, either one, the first 3 columns, we don't want to screen the case number, it's a participant number. And then these 2 are our categorical variables, so we're just going to drop those. Calculate our cutoff score here based on the big important rule, so 0.001. We're going to use the degrees of freedom as the number of things that went into that, so there should be 3, esteem, attitudes, and neuroticism. Calculate our ANOVA scores here. Our cutoff score, 1627 with 3 degrees of freedom. And we don't have any outliers. So this particular one, remember, does number of people less than my cutoff score, and we want people to be less than the cutoff score because that means that they're not an outlier. But since I've adapted this code from my data screening lecture, essentially what I'm doing here is just subsetting out the people who are bad, and there aren't any. So you'll notice down here in my environment window that I have hidden over here, my no out and no miss data set are the same size because there aren't any outliers to exclude. Blah, blah, blah. So once we get down here to additivity, we want our DVs to be correlated because the point of ANOVA is like it works better, it gives you more power if they're correlated, but you don't want them to be perfectly correlated. So this is actually a similar rule to repeated measures. We just don't want it to be 1 because if it's perfectly correlated, it won't run. So let's run our correlations here. So we're going to calculate the correlation. I'm just going to drop my categorical columns again. Use my symbols for numbers to just look for any ones not on the diagonal, or I can run the actual correlation table since it's kind of small. Our variables are somewhat correlated, some small to medium correlations. Let's plan now for the rest of those assumptions. So we're going to create a random variable because this is part of the ANOVA family, so we've got to run fake regressions to get the assumption tests. So I'm going to create a random data set. Remember the 7 here is just your favorite number, greater than 2. I'm going to calculate my fake regression based on the data set minus that case number. So I don't want to include participant number, although it won't really change a whole lot if I do. Calculate standardized or studentized residuals and our fake fitted scores. And those are just going to allow us to look at make sure the residuals are normal and linear. Okay. So under normality here, remember this is random, so you're all going to get slightly different answers, but that's looking pretty good. Maybe a small set of skew. Let's run that again, see what we get. Yeah, just maybe a touch of skew. I would say this is mostly pretty good. We have 300 people, so we should be all right. Linearity, let's zoom in. It's a little curvilinear. It's not terribly great, but it's not horrible either. So between 2 and 2, it's mostly okay. You're always going to cut linearity a little bit of slack. Homogeneity and homoscedasticity here, whoa, that's no good, right? Because it runs from about -2 to 4, this way is okay. So for homogeneity, that's not good. And we're going to be able to test homogeneity with Levene's because this is a between subjects test, but let's run one more of those. Yep, still bad. So even with multiple tries here, homogeneity might be problematic. Homoscedasticity, this is ANOVA, so it doesn't matter too much, but it's starting to look like a tint, so also not good. Okay, so we've got some problems with our variances. And that's our normal data screening setup here. So let me get through that. Now we're also going to run Levene's test. But because we're not using ezANOVA just yet, we'll have to get Levene's separately, right? Cutting and pasting here. And so it's notoriously oversensitive, remember, but it's a good place to start if you aren't sure which DV is the problem. It can also be it can end up being significant no matter what with large sample sizes. So we're going to run Levene's, but remembering that, you know, sometimes you can't do a whole lot about it. And if it ends up being significant, I would run those ANOVAs separately. You can also do some non-parametric versions of Manova. So we're going to use the car library to calculate Levene's. We could also run an ezANOVA on each DV separately. That would also work. But here's another way to do it. So we're going to do the DV column is predicted by IV times IV here. Data equals data set. Center equals mean. Okay, so remember we're changing the words here in italics. If I only have one between subjects part, you just would delete this out. We also did this in our ANOVA video, if you've watched that one. So we're going to do esteem predicted by femininity times masculinity on our no-out data set. Let's look at that one. Right, and is not significant. Now we're going to switch out and do attitude towards the role of women, also not significant. Let's do neuroticism, not significant. So we have some issues with maybe multivariate homogeneity. Each individual IV is okay though. All right, now the tricky part, setting up the Manova. So with ezANOVA, we had to set up, do this participant number thing, maybe we had to melt. But with Manova, what we're gonna do is create this DV into a separate little like kind of data frame. So we're gonna use DV equals, and I'm just gonna call it DVs for the rest of the Manova part. cbind, remember cbind is for column bind, so this is gonna put together columns. I'm going to put together all of the columns that are DVs. And it creates just a little separate data set that's just the DV. Then what we're going to do is use DV, and now here since we've called it DV, you don't actually change that particular piece of code, is predicted by IV times IV. So we're taking our IVs in one data set and predicting the entire other data set. So it's important to have them as two different data sets. This one is the original data set with the IVs, so I'm just going to say IV data set here just to make that clear. And then this fancy thing. Okay. What this does is it forces it to act like real ANOVA. Okay. So if you don't do this, it's going to give you a different type of sum of squares than type 3, and we want to make sure we stick with type 3. Okay. And so we're going to fill in the names of our IVs here, and it's going to do summed contrast. So what I did here was cbind for our 3 different IVs from our no-out data set. You'll now see the DV is just a separate little data frame over here. It's actually kind of a matrix, I guess, but either way, that's what we want. Then we're going to do DV is predicted by femininity, masculinity. That's in our no-out data set. Contrast here, here's where we filled in femininity and masculinity here. So the only thing we changed on this contrast line is fem and mask. And we saved it so that we could do something different with it. Now this is where the magic happens. This Manova command, and it's capitalized. It's one of the few ones in base R. Oh, is it in base R? Let's find out. Oh, it's in the car library. So it's one of the few ones that's got a weird capital. Remember, the view has a capital at the beginning, but very few of them start with capitals in the beginning. Okay, but this one does. So we're going to run a Manova on our output. I'm going to tell it to give us type 3 sum of squares. So all this thing is doing is, oh, and look, I even have the note right here. It's in car. Derp. All this thing is doing is changing this to Manova output from regression output. Where we talked about ANOVA is just a special type of regression, well, Manova is too, and so we're just converting it to output that is specific for ANOVA. So you see Wilks. Okay. Then, after we do that, we're going to take the summary function and do multivariate equals true. So we're going to get a lot of output. Okay, and so what you're interested in here is ignoring the intercept part, and I cut this into different pictures. When you're looking at the output here, you see type 3 sum of squares, blah, 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 intercept, yada, 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 yada. come down here to where your first IV is. That's where we want to start. So for our femininity main effect, what you want to do is scroll down here and look at your favorite DV combination option. Now, in this particular case, they're all the same. That won't always be true, but mostly people pick Wilks. So here's the first degree of freedom. The test statistics here, this is lambda, so Wilks lambda. Okay. The F value here, 7.84, are degrees of freedom for that F here, so 3 and 301. So this is your traditional F number, so numerator, degrees of freedom, denominator, so model and error. And then here's our p-value. So I've got all that, oh my goodness, so much scrolling. I've got all of that written out, and this is how we would write it up. Now, where the heck did I get eta squared from? Well, eta squared is 1 minus lambda, or 1 minus Wilks. Or if you just want to be even lazier, that is actually what Peli's is 1 minus Wilks. Okay, so this is where a 0.07 here. So the Wilks here is lambda. Sometimes people report it, sometimes they don't. Definitely these F statistics, but then eta squared is the same as Peli's. For masculinity here, we see that it's also significant. So there's significant differences in the overall global DV on femininity and masculinity. What about my interaction? Okay. There's actually no significant difference on that interaction. Okay. Right, now what we're going to do is run ANOVAs on the significant effects to only see which DVs were significant. And since this has now become a 2x2 between subjects ANOVA, what we can do is use ezANOVA. And there's a description of what all the jazz for ezANOVA. But hopefully at this point you've watched your between subjects ezANOVA. I already have a participant number, so I don't have to create one. And we're going to do 3 ezANOVAs, 1 for each DV. Remember that when you have more than one IV, it's dot to combine them together. So we've got data, DV, within subjects IV, that's your participant number. For between subjects variables, type equals 3 to make sure that we're still doing type 3 sum of squares. It's going to give me this like warning because I forgot to factor my case number. That's okay. It does not like that our group sizes are not equal, so it gives me a little bit of warning there as well. And what I'd want to do is follow up only the significant tests. So I'd only really be interested in femininity and masculinity, and I actually would ignore the interaction because the interaction was not significant in the overall Manova. So I would look here and I'd say, well, femininity and masculinity are significant for esteem. I could run that again for attitudes. They're both significant here. I'm going to run that one more time for neuroticism, and I got nothing. And so I've kind of written that out here. So I'm reminding you, ignore those interactions. So remember, these are also going to be partial etas because we're running ANOVA here. So you should have that little P in there. But what's happening is that wrong button. And then these are bold just for fun. There we go. So for self-esteem, femininity is significant, masculinity is significant, but it's definitely the bigger predictor here. I would say this predictor is not very useful. Attitudes, they're both medium, small to medium effects. And then for neuroticism, nothing was significant. Since these effects are only 2 levels, we can just look at the means. If there were more than 2 levels, then we would start having to do post hoc tests. You can look at the ANOVA guides to check those out, and we can run pairwise t-dot test. If I was analyzing that interaction, I could split the variables and run pairwise t-test. And then I just have some little notes here about how to do that in case you need to. But right now, what I want to do is just look at those effects. So for femininity, we found a significant difference in esteem. So people who have low femininity scores, that word is hard, have higher esteem. I can run my standard deviations. For masculinity, what we see is that people who have low masculinity scores have higher self-esteem. So that's why there's no interaction on this variable, is that for low groups, people have higher self-esteem. For attitudes, people who are high in femininity have higher attitudes towards the role of women. And then for people who have higher masculinity, have higher attitudes towards the roles of women. Now for neuroticism, these were not significantly different. So I would say that femininity low and high have the same neuroticism, and masculinity low and high have the same neuroticism. Even though these numbers are fairly different, they're not significantly different because of the high standard deviations. Now the only thing I'm doing in this section is I'm going to make a picture, but because H is alphabetically higher than L, it put high as our first factor. So I'm just going to reorder those so that my plot comes out with low on the left side and high on the right side, because that makes more sense. Right. So to make this graph, we're going to use ggplot. So there's some notes here on ggplot. We're going to run that cleanup code and make ourselves a bar graph. There's a whole lot of schma at this point, hopefully in my class. You guys have bar graphs down. If you're new to ggplot and bar graphs, we've got a whole separate video on it. And then some instructions here, but we're going to make some cleanup code to kind of clean up the ugly gray background. The auto comes with ggplot. We're going to put in the dataset name. We want to do IV1, first DV, IV2, so I could switch femininity and masculinity here without too much trouble. We're going to create a bar graph. So all of this code, remember, creates the bars and the confidence intervals. We're going to clean up that bar graph, give it some X and Y labels, and then just clean up the legend labels as well. And so for femininity, I can see there's no interaction because the pattern of the data is the same. There's probably a larger difference here than here, but there's no interaction because the differences are fairly similar. Then we could then plot attitudes. So this is the exact same graph. I just changed out for the word attitudes. And we get the same cute pattern. And then for neuroticism, they should be fairly equal. So they're pretty much all the same here. Look at these overlapping confidence intervals. Okay. So then I would work on writing that up. Now, when you do Manova, you do end up with lots of graphs because each DV has a separate graph. It's really hard to cram all of those things in together on one graph, and makes it difficult to read. So I always just recommend separating out those graphs. This write-up number, numbers, grammar, whew. So what you want to do is talk about data screening. So that's the first couple of sentences here. Then I have a 2 by 3 in this example that I don't even know why it says 3, a 2 by 2 between subjects, Manova. And so what you want to do when you're working on writing these up is that you're going to have the information for the Manova. So this is significant multivariate main effects were found. So this is like F for Manova 1, F for Manova 2, F for Manova 3. So we've got IV1, IV2, and IV3. Then talk about the univariate ANOVAs. So blah, 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 blah. And then maybe talk about post hocs. Alternatively, what you could do is what I've done here is talk about the univariate femininity effects. And then I have like each post hoc, and then the univariate masculinity effects. But you could also do Manova paragraph, ANOVAs paragraph, post hocs paragraph. This kind of makes more sense which, it makes more sense depending on like how you're going to follow those up. So here I just talked about femininity the entire time, so it made sense to throw them all together. But I could talk them, group them by DV as well. So a couple different ways to do this, but the main thing that you want to do here is make sure you include all of the F statistics for the Manova, all of the F statistics for those significant Manova effects, and then any interesting post-hoc effects that you found. Okay. So all that together is Manova, which is an extension of ANOVA. And so it's basically ANOVA with some extra stuff on top, and then an example of graphs and write-up.